Thank you for oh, I see. Actually, that is a smart choice. Yes, if you were not going to watch it later, you can watch it now because you're already here, and honestly, there's not much better for you to be doing except, well, it depends on how you prioritize your life. But, okay, so we're going to start with this problem, and we're just looking for the electric field at this point right here. So in order to find the electric field at this point right here, we have these two different rods. We know what the charge on each rod is. It's Q. Right, and we know these things are a height L, so that we're going from 0 to L. But the key thing here is we're going to be calculating this using what equation? Coulomb's law. This is a Coulomb's law integration problem. So we just we start from this, and Coulomb's law is E, which is a vector, is equal to KQ over r squared in the r hat direction, which just means towards or away from the other thing. But what we're doing here is actually a differential version of Coulomb's law, which means we have dE and dQ, okay? Because those are the only two things we're varying, which means for every little tiny chunk of Q, every little tiny chunk of charge, we get a little tiny electric field. So essentially, we're doing a point charge infinite number of times, okay? And so to do that, we're going to break these guys into a lot of little point charges, and I'm just going to take some sample ones right here. So these guys we will call dq, okay? Each dq thing has a length or a width or whatever of d, actually that's not a great place to put that, dy. Why is it dy? It's on the y-axis, and it's a variable, right? Because we're going to integrate along the y-axis. What are our limits of integration?
0 to L.
0 to L, right? Because we have 0 down here. This is 0, right? So we're going to integrate each of these from here to here and here to here. Okay, that's our integral, which means we start with a little chunk down here, then we have a little chunk here, then we have a little chunk here. There's a bunch of them in between. I'm just sort of giving you the lay of the land, okay? So what we're doing is for each of these little guys, we have an R, okay, that goes to this point. R is just the distance from the charge to the point, but because we have two of these, there's some fun symmetry stuff happening. If it's just one of these guys, then you just end up with an electric field that points this way, okay, your total. But because it's two of them, you're going to get one that points this way, one that points this way. Which way is our, when we add the vectors, right, you can break these into x and y. What happens to the x components? They cancel out, okay? What happens to the y components? They add together. So we know that our answer needs to point down. Oh my gosh. And we know that that means we have to have some sort of component. But I'm getting a little bit ahead of myself, so I'm going to say, okay, for each of these r's, you have a dE, right? And you have another dE over here. If I drew better, those would be more identical, but just pointing in different directions, but I'm not good at drawing, so I apologize in advance for that. The other thing is this is R, but R has remember, we can't write this in terms of things we aren't given. So we're given A, and Y is a variable we can use, but all the constants have to be given. So how do we figure out what R is?
Square root of a squared plus L squared.
This is it's Pythagorean theorem. This is always A, that's a constant. But then we also said we're integrating along Y. So this value would be Y, but remember, Y can change. A can't change, but Y can change, okay? So R is the square root of A squared plus Y squared, where A is a constant, but Y is a variable, okay? And we also have this dy that's going to come back to haunt us later, but that's where we're at for this. The other thing is for dE, for each individual dE, you break it into dEx and dEy. And as we talked about, now the one before we were talking about was just the full-on resultant vector for each thing. But on an individual level, for each of these, if you pick a little spot, you'll have an R and you'll have a dE. And it's going to always cancel the x component because of the symmetry. Okay, this is what I mean when I say symmetry is your friend. Okay, in this case, it's going to mean instead of doing 2 integrals, you only have to do 1 integral, which is much nicer because that's half as many integrals. Math. Okay, so for all of these, we just want to find, going back over to our original thing, we just want to find DE in the y direction. How many of those do we need?
2.
2. So we can either do 1 on each side, or we can just do 1 and double it. Which one sounds like a better idea? 1 and double it. And let's not do the one with the negative that's confusing. Let's do the one that's all positive. So what we want is DEY. We actually want 2 DEY, which should be equal to 2K DQ over R squared. But to get Y, what do we need? Well, we know this angle is theta, which means this angle is theta. Theta should vary too, right? Because if you have a dot here, then you have a thing here, that should be there, and your theta will get smaller as you go down the rod, okay? So that means we also need to figure out, we need Y, so is this sine or cosine of theta? Sine, so this should be sine of theta. But of course, we can't write things in terms of theta. We have to write them in terms of like A and Y. So what's sine of theta?
Y over A.
Yeah, y over r, which is a squared plus y squared. Okay, now we gotta start plugging stuff in. Oh, we're still missing one other thing. We need to worry about dq, okay? Because we need that in terms of dy. So what we want to do is dq is going to be the linear charge density. Okay, this is a line, so it has a linear charge density. What's the linear charge density?
Q over 2n. Q over L.
Just Q over A. Or sorry, Q over L. Q over L. Because each of these has a charge Q and a length L. So Q over L. Just charge over length. There's 2 of them. Remember, we're just dealing with one of them and then doubling everything. So this should look nice because you know density is charge over a length or an area or a volume. Okay, in this case, because this is a one-dimensional problem, and by one-dimensional I just mean one variable, obviously this is in a 2-dimensional space, okay? But in math, we care about the dimensions. Dimension just means number of variables. In multivariable calculus, that's more dimensions. It's not the physical space that it takes up, it's the number of variables you have to deal with. So this is a one-dimensional mathematical problem, even though it is a 2-dimensional picture, okay? Does that make sense? Cool. So we can rewrite this as Q over L, that's the density, times dy, okay? Which is neat because that means we can plug that in. So now we're going to plug in all this crap, okay? So what we have is 2K, and then we have dq, well, we know that's Q over L dy, okay? What's R squared? A squared plus y squared, which is really the square root of a squared plus y squared squared, but let's skip that step. You guys are math people. And then this sine theta is y over square root of a squared plus y squared. Okay, so I'm going to shrink this down a little now that we've kind of, can you still see all that? Even in the back? Can you see it? Okay. Yes?
Why do you need to include the sine theta?
Because we're only dealing with the y component. If you do the homework, there is a problem that's just one of these by itself, and you end up doing 2 integrals because you have to do the x component and the y component. Because you can't really do it directly. Because remember, it's a vector, so you can only add up a bunch of x's and a bunch of y's.
What I'm saying is, why do we need to consider theta?
Why do we need to consider theta? Because it's a vector. Yeah, because if you just look at the electric field from one of these, it points this way. But we're in an XY coordinate system, so that means we have to include vectors. Even if it's a DE, it's a differential, a tiny, tiny vector. To add vectors, we can only add x to x and y to y, unless we're doing Pythagorean theorem or any of that stuff. So even when we do an integral, if you're in 2-dimensional space, you're always going to have 2 integrals unless we set it up so it only goes in x and y. Yeah.
What is the principle called where like this angle is equal to this angle?
Oh.
Because it is, right?
Opposite interior something.
But,
Angles?
Because that's why that's where this comes from, right? This.
No, the r hat just says that it's
Yeah, like
supposed to be
this.
parallel to this line. Yeah. So the r hat means if you have a point charge and you have an electric field, it points out radially in all directions.
Well, you're replacing the r hat with the sine theta.
Well, actually, we're just going to add up. We're going to start from here, and for each of these, we find an r and a theta until we get all the way up to L. Okay? So to represent that, we're basically integrating both sides. This one is simple. It just becomes 2EY, right? This one goes from 0 to L. And there's a lot of algebraic simplification that we have to do, so we pull out 2kq over L, and this becomes y dy over a squared plus y squared to the 3/2. Okay, and that's all in the y hat direction. Cool? All of this stuff over here is a constant, but this over here is our integral that we have to deal with. Okay, what kind of integral is this? I can hear you, but how about in the back? What kind of integral is this? Yeah, it's a u sub, okay? Do we want to go through the u sub? I don't really like teaching calculus. No? Yeah. Okay. So, I appreciate you identifying it as a u sub. That is about as much as I care about. So, this is 2kq over L. We do the u sub. The u's like, u should be a squared plus y squared, and then du is like 2y dy. Okay, all that jazz. And then when you do all that stuff, ipso facto, you end up with negative 1 over a squared plus y squared. I'm just going to say, like, calculus happens here, okay? And if you want to practice u-subs, I'm happy to do them in non-physics time. So if you want to come to office hours and just do hours of u-subs with me, it is a fun game. But, yeah, I'm a little bit more concerned with the physics here. So even if on a test you get to this part and you're like, this is a u-sub, and then probably something happens, and let me just sort of guess, I'll give you like 9 out of the 10 points. Doing the u-sub also important. I will probably give you a u-sub, not a trig sub on an exam, just because who's got the time for that stuff, okay? If I give you a trig sub, it'll say if you get an integral that looks like this, here's the next step, okay? All right, so you plug in your L's and you end up with something that looks like 2kq. Oh, I think we lost a 2. We lose a 2 somewhere. No, we didn't. Okay. Like 1 over a minus 1 over a squared plus L squared square root.
The 2 from the du part.
Yeah, the 2y dy should.
Where did it go?
Multiply the 2 to get the du. You should have a 1/2 on the outside.
Okay. So does the 2 go? No, we need a 2 at the end still. I think it cancels with a different 2. There's a 2 here, and then there's a 1/2, and they cancel.
Yeah.
So the 2 we see here is from doubling the
Yes.
y component. Okay, we're still good. Always good to check where you're at. All right, and then last but not least, that's pretty much it. We're done. That's all. Yeah. Oh, make sure it's in the negative y hat direction. And then this is your E. We'll just call this E. So that's your final answer. Okay?
Professor?
Tons of fun. Yes.
I know because it's doubled, but why is it 2d sub y equals, why do you multiply 2 on each side? Wouldn't that just cancel out?
Oh, well, okay, we should have just written E equals, or whatever, E total. it doesn't cancel. I'm multiplying it through.
Oh, okay. So,
Yeah.
so
Don't-
you're double. You're
I'm just,
like,
that was more of a demonstration
Gotcha.
thing, but
More
yeah,
of a
you have to
visual.
do twice that to get, this isn't, it's got messy. Here, let me move that over. But what I really meant was like, E total, I'm out of space. Dang it. Nope, don't want to make that small. There we go. So like our E answer is equal to that, okay? And then we'll call this E answer. Okay, which points in the y direction. Yeah, so just to review, right? We have to figure out r, that's r. We have to figure out sine theta. The sine theta comes from, sine theta is over here. That comes from r hat. It's because it's a vector, okay? So it's always important to draw out what this looks like first. Make sure you cancel anything to make your life easier. Any other questions?
it's an ugly answer.
Okay. Do you guys want to do a curved one now?
Yeah.
Yes, whatever you put on there.
Yeah.